This is the second video on alternating series, and we're going to look at two things. We're going to look at remainders in alternating series, and then we're going to look at absolute convergence, conditional convergence, or divergence of an alternating series. The remainders in an alternating series. If an alternating series satisfies the hypothesis of the alternating series test, and let S denote the sum of the series, and S sub n denote the nth partial sum, then for any integer n greater than or equal to 1, the remainder R sub n is equal to S, the sum of the series, minus the S of n, the nth partial sum. And that's going to satisfy the absolute value of the remainder, R sub n, is going to be less than or equal to A sub n plus 1, and sometimes that's called the first neglected term. The absolute value of R sub n, the remainder, is equal to the difference between the sum and the nth partial sum, the absolute value of that, which is equal to S of n plus 1 minus S of n, that's just the A sub n plus 1, and that's equal to A sub n plus 1. Okay, so let's go ahead and do an example of that. So let's look at the sum n equals 1 to infinity of negative 1 to the n times 500 all over n to the 0.7, and we're going to find S of 4 and the error. And we say and the bound for the error. So S4 is equal to negative 1 to the first times 500 over 1 to the 0.7 plus negative 1 squared times 500 divided by 2 to the 0.7 plus negative 1 to the third power times 500 over 3 to the 0.7 plus negative 1 to the fourth power times 500 all over 4 raised to the 0.7th power. And that's approximately negative 234.4808, etc. So the absolute value of the remainder, the fourth remainder here, is going to be less than or equal to the first neglected term, which would be A sub 4 plus 1, or A sub 5. It's going to be 500 over 5 to the 0.7, and so that's approximately 162.065, etc. And that's a big bound on our error, so we could still be plus or minus 162. So we might want to go out further in our series, use a further along partial sum to get a better approximation. Okay, so we could do that. And so let's go a little bit further out. So here's the same series. So maybe we're going to use the 10th partial sum. And so I went ahead and calculated the 10th partial sum, negative 272, almost negative 273. The absolute value of the remainder here is going to be less than or equal to the 11th term in the sequence, which should be 500 divided by 11 to the 0.7, which is approximately 93.324. And so we've narrowed down the error a bit, but that's probably still quite a bit of a variance there, 93 up or down from negative 273. So what if we went a little farther? We went to S of 50, and that's going to be negative 305, etc. So the 50th remainder will be less than or equal to A sub 50 plus 1. So 500 over 51 to the 0.7, and that's approximately 31.89, etc. Let's go back to that slide there. And so we're narrowing it down. Maybe we need to go out to the 100th or the 200th in the partial sums to actually get something real, accurate. Maybe we want to be accurate within, a 100th or something like that. So you just have to go further out in the sequence. So this one seems to be a little bit slower in converging. Some series might be a little bit faster, and you only need to go out to, the 10th term. 10th partial sum would be good enough. It just depends on the series. Okay, so the next topic we're going to look at is absolute and conditional convergence. We say a series n equals 1 to infinity of A sub n converges absolutely if the sum n equals 1 to infinity of the absolute value of A sub n converges. A series n equals 1 to infinity of a sub n converges conditionally if the sum n equals 1 to infinity of a sub n converges, but the sum n equals 1 to infinity of the absolute value of a sub n diverges. So we're going to look at 3 series, I think, maybe just 2. The first one we're going to look at, well, with the series, we're going to determine whether the following converge absolutely, converge conditionally, or diverge. So we're going to look at that same 2 series we did in the previous video. The sum n equals 1 to infinity of negative 1 over n, negative 1 to the n over n, and the sum n equals 1 to infinity of negative 1 to the n all over n squared. And we applied the alternating series test on both of them. And so they will converge by the alternating series test. And so that'll give us at least conditionally convergent on both of them. However, the first one, the number 5 there, the problem with that is the sum n equals 1 to infinity of 1 over n. That would be the absolute value of the terms in the sequence. That is the harmonic series. That's a p series, and that diverges by the p series test. The p being 1, and that is less than or equal to 1. So that one's conditionally convergent, where it converges at an alternating series, but if we drop the alternator, it's not convergent anymore. Now the second one is going to converge absolutely. So we already knew it converged conditionally with the alternating series test. Now if we look at the absolute value of the sequence, that's going to be the sum n equals 1 to infinity of 1 over n squared, and that is a convergent p series with p equals 2, and that's greater than 1. And so that is an example of what is different between conditionally convergent and absolutely convergent. And certainly we could have a series that just flat out diverges. And that'll be coming up in the next video. We'll work out a couple more examples. So stay tuned for the next one.